Welcome back to the deep dive. Today we're going to try to wrap our heads around some seriously complex physics. We got this paper on the Bethe equation at Q0, and honestly, it looks kind of intimidating.
Yeah, it's definitely niche. We're diving into the deep end where quantum mechanics meets something called mathematical representation theory.
Whoa, okay. And the paper mentions the combinatorial completeness of the string hypothesis. Is that like a theory of everything kind of thing?
Not quite a theory of everything, but it is about understanding the energy states of certain quantum systems.
Okay, so like instead of the entire universe, we're figuring out how, a single atom vibrates or
You
something?
got it. It's about mapping out those vibrations, those quantum states, with incredible precision. This equation, it gives us the tools to predict and understand those states.
I'm intrigued. But the paper's abstract, it mentions a linear congruence equation. And now I'm flashing back to high school math class.
Think of it like this. Imagine sorting objects into boxes, but there are very specific rules about which object can go where. That's essentially what that equation is doing. It's a bit like a mathematical puzzle, really.
Okay, I kind of see that. And what about weight multiplicities? Are we talking about how much a quantum particle weighs?
Not exactly. It's not about physical weight in this sense. Weight here is more like a label, a way to categorize different energy states within our system. Imagine each of those vibrations we talked about has a unique label.
So it's not really weight like we think of it, more like categories or something.
Right. And weight multiplicities, those tell us how many vibrations share the same label.
Okay, so it's about understanding the distribution of these energy states, not their actual physical weight.
Got it. Now, the paper keeps mentioning string solutions. Are we talking about actual strings here, like on a guitar?
You're closer than you think. These strings are actually complex mathematical functions, and they help us describe the behavior of our quantum system. The research here zeroes in on what happens when a certain value, we call it Q, is set to 0. And that's when these functions become super interesting. They simplify in a way that reveals a lot about the system.
So these strings, they're like a secret code we're trying to crack.
Exactly. And to crack this code, we need the string center equation, or SCE. That's our tool for finding the most important characteristic, the center of these string solutions.
So the SCE helps us read the map, so to speak. You could say that. But here's the thing. Sometimes the equation gives us solutions that are like detours or dead ends. We call those inadmissible or diagonal solutions. What we're really looking for are the admissible off-diagonal solutions. Those hold the real key to understanding the system.
So it's like we're panning for gold. We have to sift through a lot of dirt to find those little nuggets of valuable information.
Exactly. Luckily, we've got a mathematical tool that helps us with that sifting.
Oh, what's our secret weapon?
It's called the Möbius Inversion Formula.
That sounds intense.
It's a really cool technique that helps us filter through all the solutions from the SCE and pick out just those off-diagonal solutions, the ones that matter.
So the Möbius inversion formula is like our metal detector, helping us find the real treasure. We've got our map and our metal detector. What's next? Okay, so we've got our map and our metal detector. What do we do with them?
Well, the paper actually walks us through an example. They use what's called the spin-a-half XXZ model.
Catchy name. What's that all about?
It's a way to describe a specific type of quantum system, one that's used to study magnetism.
So we're using math to figure out how magnets work at the tiniest level.
Exactly. And remember those weight multiplicities we talked about. This model shows us how to calculate them. We use the string center equation, sift through the solutions with our Möbius inversion formula, and boom, we get our weight multiplicities.
So it's like we're putting all these tools together, and they actually work.
They do. And the cool thing is, the researchers don't just stop at this one example. They generalize the whole process.
Generalize. Yeah.
We're not just talking about understanding the energy levels of one specific magnetic system. We're talking about a framework for understanding a and y quantum system.
Whoa. That's a pretty big deal, right?
It is. And to do this, they introduce something called generating functions.
Generating functions. What are we generating? More equations.
Think of them like information capsules. Each generating function holds a ton of information about our quantum system, all packed neatly into a single expression.
So instead of looking at each energy level one by one, we can use these generating functions to get the big picture.
Exactly. It's way more efficient. And the way we build these generating functions is actually pretty clever. We use a mathematical trick involving something called a residue.
Residue? Like what's left over after a meal?
Not quite. It's a specific value we can pull out from these generating functions. Imagine the generating function is a giant cake with all the information we need. The residue is like a slice of that cake, and it still has all the important flavors, all the information we need.
Okay, so we use residues to get the good stuff out of our generating functions. What then?
Remember how we're focused on finding those off-diagonal solutions, the really valuable ones? Well, we use a special type of generating function denoted by the letter R to represent them.
Okay, so R is like our VIP section of solutions.
You could say that. Now, here's the really interesting part. The researchers found a direct connection between R, our VIP solutions, and another type of generating function denoted by K. We can actually express R in terms of K.
So we're linking these two different ideas, R and K. And doesn't K have some special meaning too?
It does, and that's where things get really exciting.
Okay, so we left off with this mysterious K function. It's connected to our VIP solutions, the R function. What's so special about K?
Well, K gives us the multiplicity of irreducible components.
Say that again, but slower this time.
It tells us how many fundamental building blocks our quantum system has.
So like if we're building a house, K tells us how many bricks we need.
Sort of. Each brick is a fundamental part of our system. Now, here's the mind-blowing part. The paper proves that R, our VIP solution function, it directly connects to something called the character of the quantum space.
Character, like my quantum system has a personality now.
Not exactly. Think of character as a unique fingerprint, something that identifies our quantum system.
Okay, so it's less about personality, more like an ID card. And we're saying R is connected to this ID.
Exactly. It means our math, it's actually reflecting something real about the quantum system. And get this, remember we started out trying to understand those energy levels. Well, the paper found that under certain conditions, the R function, it lines up perfectly with the weight multiplicities of those energy levels.
Hold on, so all these equations and functions and residues, it all comes back to those energy levels, full circle.
Exactly. And that's the beauty of this kind of research. We go on these crazy mathematical journeys, and they lead us to real, tangible insights about the universe.
This deep dive has been wild. We've gone from basic equations to string solutions, generating functions, even quantum fingerprints. My brain's a little fried.
Mine too. But you know what? Even with all this incredible work, there's still so much we don't know. Like, why does this connection between our math and those energy levels exist? Is it just a coincidence, or is there something deeper going on?
It makes you think, right? There's always more to explore, more to uncover. And on that note, I think we've done enough deep diving for one day. Listeners, thanks for coming along on this wild ride with us. Until next time, keep those minds curious.